So what is pdqsort or pattern defeating quicksort? It's a general purpose unstable comparison sort. So it does not preserve the order of equal elements like some other sorts do. And it only uses comparisons to determine the order. It's an introspective algorithm. So it is not only quicksort, it switches between different algorithms based on various heuristics. It has various novel and known tricks to handle certain patterns in the data that we'll talk about. And it have an open source C++ implementation in the aforementioned GitHub repository. So just to clarify, so everyone is on the same page, very briefly, what is quicksort? You choose a pivot displayed in red here. You partition the array so that the pivot is somewhere, hopefully in the middle. Everything that's less than it is on the left. Everything that's bigger than it is on the right. And then we recurse and repeat. So that's the basic idea of quicksort, and we're now gonna look at how pattern defeating quicksort improves on this. First, I have to introduce my performance assumptions for this talk. So what I consider in scope, at least when I designed pattern defeating quicksort, I'm assuming that our data is in memory, that we have random access to it. But random, like even if almost all memory accesses are sequential, so it's not like we're jumping all over the place. I'm expecting our comparison operator to be cheap. So if your comparison operator involves calling back to a human, you probably want a different sorting algorithm. And I'm also expecting our types to be cheap to move. So if you're sorting, I don't know, 1,000-byte arrays or whatever, probably not in scope. So essentially a traditional system sort, like you would get if you call std sort. So I'm going to be talking about the following optimizations in pdqsort. I'm going to talk about the pivot selection, the branchless partitioning, the insertion sort base case. Well, you can read it yourself on the slides. There's a lot of optimizations. Some are more important than others, but that's why I call it the bag of tricks. There's not one thing that you can point at that's pdqsort. It's a whole collection of different optimizations. Finally, my experimental setup. I did all the benchmarks shown in the slides on my new MacBook using Clang, latest install. I also show briefly like the CPU in an Apple MacBook. It is a bit weird. It doesn't have an L3 cache. It has an OKL1 cache and quite a large L2 cache. That actually matters a lot for the benchmarks, like where do you pass the cache threshold. And all of my figures are medians over repeated experiments that are single threaded. So my main takeaway of this talk is that comparisons do not tell the full story of sorting. They aren't even the protagonist of the story, essentially. So I have 3 numbers on the screen here. One for heap sort, one for pdqsort A, and one for pdqsort B. And what is this number? Well, this is the amount of comparisons that you need to sort 2 to the 24 uniformly distributed 32-bit integers. I'm not going to keep saying that. That's like almost everything in this talk. And we divide how many comparisons that takes by n log n, because, well, we expect it scaled like n log n, so that makes the numbers comparable across sizes and stuff. And we see that heap sort does quite a bit worse than pdqsort on this regard, but there's no difference between pdqsort A and B. So there was a 61% improvement and then 0%. But then if we look at actual runtime in nanoseconds divided by n log n, we see that this 60% improvement in runtime suddenly becomes 174% improvement. And even though there was no difference in comparisons between pdqsort A and B, it's almost 3 times faster. So why? Well, the difference between pdqsort A and B is that one is branchless and the other one isn't. And heap sort does a whole lot worse than pdqsort. Well, we saw 60% of that was due to comparisons, and the rest is mostly cache misses because it jumps all over the place. So there's a massive performance gap between these 3 algorithms, and comparisons doesn't tell you that at all. So traditional old academic exercises regarding sorting are all mostly about comparisons, but I don't know, it's really not the full story, and probably not even the most important thing on modern hardware. So I want to talk about branchless or partitioning. I don't know if I pronounced that person's name right, but yeah, branchless partitioning. And the idea is that if we've identified a pair of elements, so first of all, Horde partitioning is we have a pointer on the left and a pointer on the right. We find a pair of elements that should be on the opposing side of the pivot. We swap them, and then we keep moving the pointers until we identify another pair. We swap the pair, etc. So the idea behind branchless partitioning is that every time we identify a pair of things that need to go on the other side, we don't swap them immediately. We just push the offsets that they are into an array. And then we keep doing that until our little buffer of offsets is full, and then we swap the whole buffer at once. And you can do this branchlessly. So in using this example, you just constantly overwrite the last slot in the offset table, and then you increment the length of the offset buffer if the comparison fails or is true, depending on what you want to do. So that's completely branchless. You can also loop unroll this really well. There is a data dependency between iterations, but you can apply tricks to help that, but I didn't find it to be worth it. And on top of that, because we are not doing swaps now, we have buffers of elements that we want to swap between. Instead of constantly having to move into a temporary, move over, move temporary, back over, which is usually 3 moves per swap. Now we only need to do 2 moves per swap, essentially. So it's also less data move. This isn't my idea. It's by Stefan Edelkamp and Armin Weiss, block Quicksort. How branch predictions don't affect Quicksort. Very important paper, and is a massive, massive, massive speed up. Even like they reported 80% speed up, and I found similar numbers back on my old Intel machine. Now that I reran the benchmarks on my new MacBook, the performance difference is even bigger, probably because the branch predictor is worse in the MacBook, but I don't know. Then I want to talk about pivot selection, and for this I pulled an old graph from my paper that I think is very important for understanding why Quicksort is generally so fast, and how pivot selection, how you should design that in Quicksort. So this graph on the x-axis, we have a mysterious value called P, and P is basically how good our pivot was. So 0.5 means 50%. It means our pivot was right in the middle. 0.1 would be that the pivot is like roughly 10% towards the array after partitioning. In this scenario, we're assuming that we through some magic, we consistently choose an equally bad or good pivot. So P equals 0.1 means that every time we do a partition operator, we magically chose an operator, a pivot that was at roughly 10% in the data distribution. And here we see that, okay, well, 0.5, we always choose the perfect pivot. If that is unit in terms of comparisons, or well, operations, it's all the same in this case. Even if we choose a pivot, consistently choose a pivot, that's roughly around 12% of the array, so quite a poor pivot choice. We're still only half as fast. There really is a performance cliff after that. So if you consistently choose like the smallest element in the array to pivot, you go quadratic. But if you just choose random pivots or randomly sampled pivots, it really doesn't matter all that much. Quicksort is just really fast, even with relatively poor pivots. So to that end, you could choose always the median, and then you always get a perfect split, but that's way too expensive to compute. And it's also a chicken and egg problem. If you look into how medians are actually computed, people generally use quick select. You can approximate by choosing the median of 3 elements. So, and then just using that as your pivot. There's also a thing called a Chuki's, I don't know how to pronounce that person's name either, Chuki's ninether, where you choose the median of 3 times, and then you choose the median of those 3 medians. So it's 3, 3, 3, and then the median of those. That's what I do, kind of. I'll talk about more on the next slide. But very important to keep in mind here that sample position matters. It doesn't matter if you're doing if you're sorting uniformly random data, but later in the talk, we'll talk about patterns. And if you're talking about an ascending case, you probably want to be sampling from the first, the middle, and the last element, so you get a perfect pivot in the middle. So the sample, if you're expecting to be patterns in your inputs, the sample position actually does matter. So here I'm talking about those approaches. So here you can either choose the first pivot, or the median of 3, or the Chuki's 9th, and then I have a mysterious method called adaptive. We can see that there's modest performance improvements, especially choosing first, which, since we're sorting uniformly distributed integers here, first is essentially picking a random pivot. The median of 3 is quite a bit better, 7.2% less runtime. The Chuki's 9th is only a little bit faster, but I found that the overhead of choosing a better pivot, because you're doing a median of 3 times, was not worth it for smaller arrays. So that's what the adaptive is. If the input array is bigger than 128, we should do the Chuki's 9th. Otherwise, we only do a median of 3. And that was an actually bigger improvement over just doing Chuki's 9th in the first place. In general, this is a pattern you'll notice with Quicksort, is that the performance on small arrays matters, because we're a recursive algorithm. We're actually spending most of our time in the leaves. So you always want to be optimizing for the small case as well, because you'll always end up in the small case. And that's why adaptive and introspective algorithms are very important for Quicksort. And to that end, I come to what the insertion base case. So every recursive algorithm needs a base case. You could do Quicksort all the way down to when you get to one element, which is trivially sorted. It really complicates your implementation, because you don't want to have to deal with out of bounds for median of 3 computations and stuff. And you don't want to do it in the first place, because switching to insertion sort for small arrays is faster, both in comparisons. So I found in my experiments that switching to insertion sort when the array size is 12 or less, actually is just always faster. It minimizes the amount of comparisons compared to only doing in Quicksort. But I found that even though the number of comparisons goes up a bit again, if you choose a larger threshold, the runtime keeps going down up until a certain point. So in my original implementation, the one that's still on GitHub, I used k equals 24. In the experiment shown in these slides, I chose k equals 32 because it was still a little bit faster. After that, the benefits really are diminished to almost nothing. Honestly, there's no right or wrong choice here. It all depends on how expensive you expect your comparisons to be. In this case, it's just an integer comparison. If you expect a more expensive comparison, like you're comparing tuples of integers or pairs of integers, then you might want a smaller k value. What I noticed in the libc++ source code is that they do adaptive, they make this threshold adaptive as well. If you're just sorting integers, I believe they use 32, but if you're sorting strings, it goes back to 8. Probably 12 would be a better value, as these experiments show, but yeah, if your performance assumptions are different than just sorting small integers, you probably want to hover around 12 for your threshold. pdqsort is a comparison sort. So if you can see, we have can you guys see my cursor, by the way, or not? Either way.
Yes, we can.
Oh, okay. Yeah. So as you can see, you can offer a general comparison function to pdqsort, which is very flexible. Just defaults to standard less. So if you're sorting integers or your objects has a custom comparison operator, you don't need to do anything special. But like std sort, pdqsort assumes a strict weak ordering, which is these assumptions about your comparison operator. And violating these assumptions is undefined behavior. Like it could be a buffer overflow, or it could be anything. Nans violate the assumptions of strict weak ordering. So if you have a vector of doubles that contains nans, sorting it is UB. That could be a explosion. Why? Well, assuming that these identities hold allows you to eliminate bounce checks in the most tightest core loops of Quicksort. and insertion sort. Because you can assume that a previously sorted element prevents you from going out of bounds when doing a scan. And this applies to not just my code, also all the implementations I found in pdqsort, both libc++ and lib standard C++. How much does it actually benefit? Well, I found across a variety of sizes and variety of, like, either I have branchless pdqsort or the branchy variant. I found that it only really matters for like the larger sizes, and only for the branchy variant. The branchless variant is really not affected by it much. And not doing this optimization means that I'm 9.6% slower than pdqsort. If I do the optimization, I'm within 2%. When we're assuming the branchy path. If you're a security researcher, you can find CVEs here. This is bad. I don't want to be doing it, but I also don't want to say, yeah, use pdqsort. It's only 10% slower than pdqsort. So I kind of feel my hands are bound. I want to be a drop-in replacement. So they do the optimization, I do the optimization. The standard says it's all kosher. You can do, if you're comparing doubles, you can do a branchless operator that works for nans. That's the total comparison operator, but I don't know, I'm just not happy about the situation. But it is a relatively important optimization for the branchy path. All right, now we get to the second part of the talk. This was all just straight make it go fast. Now we're going to talk about patterns. So why is it called pattern defeating quicksort? There are a couple of patterns I identified that I conjecture as common in real world data. And they're listed here on the slides. And we're going to discuss them one by one to see what pdqsort does to defeat those patterns. Because most patterns, going back to our previous graph here, most patterns really don't matter. Like if your pattern always makes you choose the perfect pivot, it's only a little bit faster than a random pivot. But if your pattern in the data consistently makes you choose the worst pivot or a really bad pivot, your performance explodes. So Quicksort really doesn't exploit patterns so much as that it wants to defeat them. It wants to get rid of them for the most part. First pattern here I'm going to talk about is low cardinality. This is actually more exploiting than defeating. Well, depending on, okay, I'll get to that. Even though your data set might not necessarily be low cardinality, whatever you're sorting by might be low cardinality. So for sorting, it's actually a relatively common case. Like you might be sorting songs, but you're sorting them by duration that's rounded to the second. And then all of a sudden, there's really not all that much variant. Most will hover around 2.5 to 3 minutes. That's not a lot of potential different values, et cetera, et cetera. So how do I solve this in pdqsort? This is a novel idea only found so far in pdqsort. I introduce a new partitioning rule that's a bit rough to get your head around, but it's actually conceptually quite simple. We compare our pivot that we chose to the element before our current subarray in the recursive call. If it doesn't exist, we always use partition right, the normal case, but we compare to the before. If they compare equal, then we do what's known as a partition left that puts equal elements to the left of the pivot. Otherwise, we do a partition right, where it puts the elements equal to the pivot on the right. And I have this visualized. So we have our current recursive call, and we have an ancestor pivot. Since we are assuming that this is a sub-recursive call, so from an earlier call, we know that the element just before it must have been the pivot that was chosen in an ancestor. Doesn't necessarily have to be a direct parent, where we got put on the right. So all the elements that are equal to 1 were put on the right back then. We also choose our pivot using median of 3. So these are our candidate elements, and then we did our median of 3 and we swapped the pivot to the front. So now we have our red pivot here. And we check if these two are equal. In this case, they're not. So we're going to put equal elements on the right. So here we partitioned the array, and all the equal elements, so all the 7s, were put on the right if they weren't already. And now we recurse. So we find that all the stuff on the left is less than 7. So that's a recursive call. We're not going to look at that. That's solved. And now we're going to recurse on the right array. And again, we're choosing a pivot, a median of 3. So here are 3 sample positions. And we find that the median is 7. So we choose that, move it to the front. And now we do this comparison again with the element right before the recursive call. In this case, they are equal. In this case, we do again a partition operator, but we put all the equal elements on the left of the pivot. So then it ends up looking like this. And if you do some thinking about it, all the elements that are less than or equal, well, if they were less, they must have already been handled in this block. There can't be any elements that are less. So less than or equal is actually equal. And as you can see, this partition operator that put all the less than equal elements on the left made a block of all equal elements. And we can deduce that they must all be equal. So we don't recurse on that subarray. We already know that's done. And we only have to recurse on the right. This is the partitioning scheme that pdqsort uses. And it's O and K. If you have K distinct values, you can actually prove that each distinct value can only be chosen as a pivot twice at most. And well, there's N operations for a partition operator, so it's O and K. There's an upper bound. It doesn't mean that it becomes very bad. It just means that it can't be worse than that. It doesn't use any 3-way comparisons or ternary quicksort. There are previous comparison schemes where like you compare to here and then you compare to this one, and if it goes in the middle, you can check later if the whole middle block is equal. There's also no like 3-way comparison. So at least in C++, in Rust it's a bit different, but in C++, the comparison operator is always just a less than, and performing a 3-way comparison generally actually just means that you're doing 2 comparisons. So it could be doubling your comparison cost. It not only handles and sorts low cardinality stuff, but it also detects long runs. So we don't recurse here, but we could do something here to maybe break ties or something similar. So it also detects the long runs. It also works if only a part of your data is low cardinality, and our overhead is only 1 extra comparison per recursive call. So it's only having to do this 1 extra check. So it's very low overhead. Our next pattern is pre-sorted and mostly sorted. And I have a little example for that. So we have a guy named John. He works at some corporation and he's tasked to implement a new feature. And for that feature, he needs to maintain some ordering on elements. And there's 3 options. You can use a B tree. You can use a smart priority queue, or it can just repeatedly push to a vector and call std sort on it. All right, place your bets as to what he's actually going to do in reality. So I actually think that mostly sorted or already sorted data is actually one of the most common inputs to a sorting algorithm in the real world. I don't actually have research to back this up. I haven't gone out and done surveys or looked at GitHub code, but I just can't imagine anything else really. So I think it's an important case to handle for a sorting algorithm. To do this in pdqsort, I have an idea due to Howard Hinand implemented. And during partitioning, when we detect a perfect partition, meaning that we never swapped any elements, we just scanned through the array and we found it was already perfectly partitioned according to the pivot, which is very rare to happen in any sort of random case, like to have an already perfectly partitioned array. We do an optimistic insertion sort. So we just, on the whole array, we just start an insertion sort and we keep doing that. And then if it succeeds, we're done. We're great. For the ascending case, you just do a scan and nothing had to be moved or out of place. We're done. That would only handle the ascending case. But again, it could be that like 3 elements were pushed to the array and then we called sort again. So it does allow you to move 8 elements to the correct position. But if it detects that there's more than 8 elements out of place, it will abort the optimistic insertion sort and we just go back to pdqsort. So this handles the ascending cases. It handles the descending cases. It doesn't handle it immediately because first we do have to do a lot of swaps, but then on the second iteration, it will trigger this detection. So it handles those cases and it handles the push a couple elements and then sort again. So I have a couple patterns here that I benchmarked. against lib C++. So what you get in standard sort, at least on macOS, the branchless variant of pdqsort, and IPS40, which I think is our main competitor for fast sorting. I'll talk more about IPS40 in a bit. And I have some patterns here. So random, we already saw. Mod 16 is, so there's only 16 distinct values. Half random and half mod 16. So half of it is just completely random, but the other half is low cardinality. The ascending case, descending case, and our earlier scenario where John pushes a couple elements and then calls sort. And what I like to notice is that at least modern sorting implementations, these are all modern sorting implementations, they actually all handle these cases. If I included lib standard C++ in this thing, so if you compile with GCC on Linux by default or MinW, it would get bullied because it misses a lot of these optimizations. But these all have these optimizations, but they can be quite fragile. For example, IPS40, sure, it handles the ascending case quite well, but then if you append 2 elements and call sort again, suddenly your sorting algorithm is like 50 times slower. So yeah, fragility is a big problem with handling these good cases and patterns. And even though I didn't show it in this little table, the same holds for pdqsort. If you append more than 8 elements, it will get a lot worse than the speed up we see here. But in general, we see quite a good speed up for all of these patterns compared to the random sorting case. Yeah. And oh yeah, the green thing I highlighted here is just to really show that this optimization with this out of order append actually makes it like 4 to 7 times as fast as not doing that for John in our example. So another problem is what I noticed is self-similarity. I didn't want to include the slides because slides generally don't like GIFs in my experience, but there's a really nice program called The Sound of Sorting. You might have seen the YouTube videos. It visualizes how an algorithm sorts. And in the past, I've played a lot with that in pdqsort to actually like visualize what it was doing. And I noticed that if there was a bad input case for pdqsort, it would generally be because it's repeatedly essentially sampling from a self-similar partition. If you choose a bad pivot, let's say you choose a pivot that only caused 1 swap, and then you choose a pivot on that array again using the same pivot selection scheme, you're probably gonna end up with a similarly bad pivot. So it's like, it's all good, and then suddenly you're quadratic on the bad input case. So you really have to defeat that. And the way we do that in pdqsort, I don't have a separate slide for that. We introduce fresh pivot candidates. So we know what our sample positions are, where we choose our median of 3. If we detect a bad partition, so a partition that I think I defined a bad partition exactly on the red area of the graph here. So if we detect a partition that was more than 10% roughly, like worse than 10% roughly of the array, then I can call the bad partition, and then we do some swapping of elements. I did it deterministically, which honestly only shifts the bad patterns from one case to another case. The Rust implementation, I'll talk more about that later, does it pseudo-randomly, which I think is actually probably a better idea, revisiting it now. I didn't like it in the past, but thinking about it now, I do think it's a better idea. And finally, malicious inputs. McIlroy wrote a paper about this in 1999. He came up with a clever technique to construct malicious inputs for Quicksort, essentially by having 2 values in an array, gas and frozen. And your gas values, when you compare 2 gas values, it will always choose the worst case and freeze one of them into a particular concrete value. So it basically is being very shady about what the exact values of elements are until you actually compare them, and then it will always choose your worst case. And it doesn't need to inspect your algorithm for this. It's actually quite clever. But the resulting, you only have to run it once. The resulting input distribution that you get is always a bad case. So you could feed it to someone in a text file or in the HTML form or whatever. And I use this technique to find that the lib C++ implementation was actually quadratic. It didn't have a fallback algorithm. And then they fixed that, 7 years later. And then I found the same bug in their standard env element implementation. So we'll find out when that gets fixed. How do we handle that in pdqsort? Well, if we detect, once again, those bad partitions, which we already detected earlier, we just increment a counter. And the counter is per recursive trawl tree. So if you view the call tree, it increments the counting for that and all the things below it. If the counter beats a log to n threshold, we switch to heap sort. Heap sort, as we saw earlier, is quite a bit slower, but it's not quadratic. And we're basically giving up and we're saying, well, we want to guarantee n log n. Let's switch to heap sort. In my experience, for random data, it never triggers. It just doesn't trigger. It's only specifically like very bad patterns or malicious inputs that this triggers on. But I do still think it's important to include it in our algorithm. Again, this is also not a new idea. Lib standard C++ does it right, and it implements intersort, which is just like pattern defeating quicksort, quicksort plus insertion sort plus heap sort. But what they do there is they just have a maximum call depth, which I think is like 2 log n. And even though it really doesn't matter all that much, I think this approach is a bit better because we're actually looking at whether we're making progress or not, because we can switch to heap sort earlier on bad cases. And if we have a bad start on an input, but then we're running fine, we don't then still hit the maximum call depth. So I think it's a ever so slightly cleverer scheme, but I doubt you'll ever really see it in any benchmark that actually matters. Then I have a quote from Andy Pavlo from his course. Quicksort is almost like the pickup truck of sorting algorithms. It can handle almost everything pretty good, but certainly you can do better. So how can you do better? I have a whole bunch of things. If you need a stable sort, so one that preserves the order between equal elements, pdqsort is literally unusable. So I have the hard requirements marked in red. You can't use pdqsort. You probably want merge sort. Merge sort is all right. Now that you want input independent sorting times. So if you're doing like a cryptographic application and you don't want people to find out any patterns about your data because you're sorting it, you want DGB sort by Daniel J. Bernstein. You know that it's always low cardinality, like you're sorting based on yes or no. You probably want a counting sort. If you're only sorting strings, then again, you can't use the branchless optimizations, and probably you're better off using radix sort. If you want to minimize the amount of comparisons that you're making, because your comparisons are very expensive, you want merge insertion sort. If you want to minimize the writes, etc. You can read the slides. One important competitor is IPS40. I mentioned them earlier. I believe that they are state of the art. They are doing what's known as sample sort, which is essentially quicksort, but you build up a little tree of pivots and then you sort each value according to a tree. It's very cache efficient. It's very good for modern hardware. It's very parallel. It's great work. In my benchmarks on my little MacBook, they weren't faster, even for large data sets, but on another machine I tested, they blew me out of the water. So really, your mileage may vary, your mileage will vary, but I do think they are more sophisticated, and it's a very interesting technique. But they are really focused on very large data, like still fitting in memory, but nowhere near cache. So if for smaller arrays, maybe not so much. Finally, let's say you do want to use pdqsort, where can you get it? Well, on C++, there's my implementation on GitHub. You can also find it in Boost. Most people have heard of the Boost C++ libraries. It's there, Boost sort, pdqsort. A guy named Peter Lamech, I found out, made a formally verified implementation of pdqsort. I don't know how that works or what machine that runs or what Isabelle LLVM is, but I think it's very cool. So go check it out. Finally, if you're using Rust, you're already using pdqsort because it's the standard sorting algorithm there for the unstable sort. Not implemented by me, but implemented by Stepan Glavina. And that was essentially my talk. Are there any questions?
Thank you very much, Orson. Are there questions? From the big room. What do you consider yourself the most crucial contribution of pdqsort?
Well, I actually used to consider it my my very clever partitioning algorithm for handling equal values. But then I actually, when I redid the benchmarks just now, I actually realized that the optimistic insertion sort case also actually kind of takes care of it. It really doesn't show up here that all much because the data moves are very cheap and the comparisons are again very cheap. So it really doesn't end up mattering much. You can do, again, you can detect it, so it's very good at that. So it's academically very interesting. I'm still very proud of it, but it doesn't end up mattering that much in the real world. Beyond that, I can't say like it's just a bag of tricks. It's the collection, it's the collective. Do miss any of these tricks and you're gonna suffer worse performance, sometimes significantly. So collecting the bag of tricks is really important to get a good algorithm for a lot of different cases.
That is actually an interesting observation as such. Yeah, indeed. Other question.
Yeah, I have a question. Well, a great talk, Orson. Really liked your slides. You said there's a CV waiting somewhere with sorting of NAs. And I was a bit fussy. That was something that existed generally in the STD sort, or was that something that you found only in specific ones?
I mean, I looked at the implementations. I didn't actually create test cases that trigger it. I looked at the implementations, and they all eliminate bounce checks in their tight loops because, again, it gives a significant performance win. And nans are just my like example as stuff that people don't realize violates these assumptions. If you use custom comparison operators, it's easy to blow these out of the water. You can easily make an evil comparison operator. Sure. And you don't even need to be evil. Like I think a very common mistake is when you're comparing a pair of elements. Well, you first have to check for equality and only then do the second comparison. People mess it up all the time. It's easy to violate this. But again, I didn't make any like proper test cases that trigger this into like a CV. But I do think like either through nans or through someone doing a custom comparison operator, it's possible to trigger UB here.
And this was in the standard library, already. That's not something that is specific to one particular compiler or something like that.
I checked lib standard C++. I checked lib C++, so it's Clang and GCC. I didn't check MSVC. I still have to do that, but I wouldn't be surprised if they also have this problem.
Okay. Maybe it's a fun project for our friends from the security group. Thank you.
Yeah. Yeah, so, but as I said, like I feel my hands are a bit tied. Like I don't want to be doing this. I don't want to have make a sort call UB because your comparison operator is a bit wonky. But yeah, I mean, I also don't want to say, look, I'm slower than STD sort, but by like 9.5% or something. So yeah, it's rough. The Rust implementation doesn't have this problem because their safety is key. If there's no other questions.
Further questions. Well, I have I just got triggered by the branchless partitioning,
Mm-hmm.
and I wasn't aware of that block partitioning yet, so I want to look into it. There is some work out of the group, and I'll put it in the chat for a minute. I'm not going to look into it, but it was ever interesting. So there had been some work on doing a predicated partitioning in the context of database cracking. So maybe as a, we could, if I find the time, I will look into it and compare those two, or try to think about those two, but I cannot think about it right now.
Yeah. This group calls it predication. I still use branchless partitioning. It's essentially predication, and I didn't include it in the slides because I was worried about going over time. I did come up with a very clever trick to get rid of this data dependency, because here again you're constantly writing into the same slot, but if you were to like loop unroll this, you can't like compute the later things because it depends on num-l. There's a data dependency from line to line. I did come up with a trick to get rid of that, involving a small lookup table to essentially insert 8 elements into this buffer at once. But in my benchmarks, at least the ones I did a couple of years ago, maybe things have changed now, it was slower. So that's why I also didn't include it, because it's not actually in the source code.
Since you already do some detection of certain scenarios and try to handle those, well, the patterns, and you have your list of cases where pdqsort is not applicable or not advisable, could you envision the and I dare to use that name borrowed by somebody else, general sort algorithm that would automatically take over and make these decisions which one to choose on which kind of scenarios, including all the other sort algorithms under the hood, and improved versions and branch-free versions of those as well?
So I really don't think so, because at least like the most of these alternatives here are not so much input distribution dependent as they are more like input type dependent or criteria dependent. So let's say you're using some kind of like tape storage where you have to like move in a different tape or whatever, or some flash that you can only write 1,000 times to before the cell is busted. You really want to minimize the amount of writes you do. Like all the work is fine, but you want to only do 1 write per element, for example. There's no sorting algorithm, like nothing can detect that. You'll just have to instruct it or like, so I don't know. Most of these things are just too specific, I would say, or straight up impossible to detect. So I think the human will have to stay in the loop essentially here.
Okay.
Our technology is not sufficiently advanced to
like
our entire programming world essentially.
Okay, are there more questions?
Doesn't seem to be the case.
If not, indeed, thanks again. Awesome. Thanks everybody, and
Thanks.
see you guys around.
Okay, have a good evening.
Have a good
See you.
evening. Nice
See you.
evening.
Thank you.
Bye.